Let's have the washer method. Let G sub 1 and G sub 2 be the graphs of two functions f sub 1 and f sub 2 respectively. Now consider the region bounded by G sub 1, G sub 2, and the lines h equals a and h equals b. This region is represented by the area FCDE. If this area is revolved about the line H, a solid S is generated. Suppose we construct n rectangles in the area FCDE. If this area is revolved about the line H, then each rectangle will sweep out a washer-shaped solid whose volume is the difference of two circular disks. A typical rectangle is shown whose upper and lower bases are L sub 2 away from the horizontal line H and L sub 1 away from the horizontal line H. To revolve this, we get a solid of revolution whose upper base is L sub 2 away from the horizontal line and whose lower base is L sub 1 away from the horizontal line H. To compute or to estimate the volume of this washer, we have volume is equal to the volume of the cylinder whose length is L sub 2 minus the volume of the cylinder whose length is L sub 1. Now the volume of the washer is a variable dV since it changes depending on its length and width dx. In this case, the dx is the width of the rectangular element, and at the same time, this dx is the height of the washer. Since the volume of the cylinder or of the bigger cylinder is equal to pi L sub 2 square dH, and the volume of the smaller cylinder is equal to pi L sub 1 square dH, then dV, which is equal to dV sub 2 minus dV sub 1, or the volume of the washer, is equal to the volume of the bigger cylinder minus the volume of the smaller cylinder. It becomes dV is equal to pi times L sub 2 square minus L sub 1 square dH. Or simply, the volume of the washer is equal to pi times the difference in the length of the upper base from the axis of rotation and the lower base from the axis of rotation times dH. Now, if we increase the number n of rectangles infinitely in the area FCDE, then we expect the exact volume of the solid to be the limit of the sum of the volumes of the washers. And we have this general formula to find the volume by the washer method. The volume of the washer is equal to pi times the definite integral of the quantity L sub 2 square minus L sub 1 square times dH from A to B. Where again, this L sub 2 is the length of the upper base or the measure of the upper base from the axis of rotation, and L sub 1 is the measure of the lower base from the axis of rotation. Now let us illustrate the general formula through this example. Find the volume of the solid generated by revolving about the y-axis, the area bounded by y equals x squared, x equals 2, and y equals 0. So first, we need to sketch the graph of y equals x squared. This is a parabola opening upward. And x equals 2. It's a vertical line. The line intersects the curve at point 24. We note that L sub 1, which is the distance of the left end to the y-axis, or say L sub 1 is the distance of, or the measure of the lower base to the axis of rotation, which is the y-axis. And this L sub 1 is equal to x. And L sub 2, which is the distance of the right end of the rectangular element to the y-axis, or say L sub 2 is the measure of the upper base to the axis of rotation, is equal to 2 units. And the width dh of the rectangle is equal to dy. If we revolve this rectangular element about the y-axis, we get a solid of revolution known as washer, whose radius of the inner circle is equal to x. Sorry, the radius of the inner cylinder, yeah, it's the same. The radius of the inner cylinder is equal to x. And radius of the outer cylinder or outer circle is equal to 2. Using the general formula, where L sub 2 is equal to 2, L sub 1 is equal to x, and dh is equal to dy, we have volume is equal to pi times the definite integral of 2 squared minus x squared dy from 0 to 4. Now, since we are integrating with respect to the variable y, then we need to replace this variable x in the integrand, this x raised to the power of 2. But how are we going to do that? We'll use the function y equals x squared. So we substitute y to x squared and then integrate it. So we have the integrand 2 to the power of 2 minus x squared. We are to integrate this with respect to y. We get 4y minus y squared over 2. And then evaluate this integral from 0 to 4. And then the volume is equal to 8 pi, or approximately 25 cubic units. Let's have example number 2. Find the volume of the solid generated by revolving about the x-axis, the area bounded by y squared equals 4x, y equals 4, and x equals 0. First, we need to sketch the graph of y squared equals 4x. It's a parabola opening to the right. And y equals 4. which is a horizontal line. The line intersects the curve at point 44. We note that L sub 1, which is the distance of the lower end to the x-axis, or say L sub 1 is the measure of the lower base from the axis of rotation, is equal to y. And L sub 2, which is the distance of the upper end to the x-axis, or say L sub 2 is the measure of the upper base from the axis of rotation, it's equal to 4 units. And the width, dh, of the rectangle is equal to dx. Now, if we revolve this rectangular element about the x-axis, we get, again, a solid of revolution known as washer, whose radius of the inner cylinder, or yeah, is equal to y, and radius of the outer cylinder is equal to 4. Using the general formula where L sub 2 equals 4, and the L sub 1 equals y, and dh equals dx, we have volume is equal to pi times the definite integral of the quantity to 4 squared minus y squared dx from 0 to 4. Now, since we are integrating with respect to the variable x, then we need to replace the variable y in the integrand. Now, to do that, we will use the function y squared equals 4x. So we substitute 4x to y squared and then integrate it. So we have transforming the integrand, we have 4 squared equals 16. Now y squared will be replaced by 4x. Since y squared equals 4x, so we have 16 minus 4x. Then integrating this integrand with respect to x, then evaluating the integral from x equals 0 to x equals 4, we get the volume of the washer, which is equal to 32 pi, or that is approximately equal to 101 cubic units. Now let's have the cylindrical shell method. Consider a region R which is bounded by a curve G, two vertical lines H equals A, H equals B, and a horizontal line H. If we revolve R about another vertical line L, a solid S will be generated, and the volume of this solid may be computed by a combination of cylindrical shells. Now, in geometry, a cylindrical shell is a solid which is bounded by two concentric cylinders. Now, we are going to partition the closed interval AB into an equal subintervals, each of length dh. Construct also n rectangles, each of which has dh for its width. The length of these rectangles is represented by this variable L sub I, because its length changes, or its length varies depending on its position on the region bounded by these curves and lines H equals A and H equals B. And the height of the lower edge, or the lower base, is represented by this variable H sub I. And the height of the upper edge, or the upper base, is equal to H sub I plus dH. Now, if we revolve this about this vertical line L, we get this solid of revolution, which is a cylindrical shell. Now, the volume uh, dV sub I of the cylindrical shell generated by revolving this rectangle about L is equal to the volume of the outer cylinder of radius h sub I plus dH minus the volume of the inner cylinder of radius h sub I. Or in symbol, we have the volume dV sub I is equal to the volume of the outer cylinder of radius h sub I plus dH. That is pi times hi plus dH square times L sub I minus the volume of the inner cylinder, which is pi times h sub I square times L sub I. Simplifying this, we get dV sub I equals 2 pi h sub I L sub I dH plus pi L sub I times dH squared. Now, to approximate the exact volume of the solid, we need to get the limit of the summation of these volumes of cylindrical or n-cylindrical shells. So we have the volume of the cylindrical shell is equal to the limit of the summation of 2 pi h sub I L sub I dH plus pi L sub I dH square, where I starts from 1 up to n, and n uh, largely increases or n approaches infinity. Or in other words, the exact volume of the solid of the cylindrical shell is the limit of the summation of the volume of the outer cylinder minus the volume of the inner cylinder. Now, let's continue. So, volume is equal to the limit of the summation of the quantity 2 pi h sub I L sub I dH plus pi L sub I dH square. Or again, this quantity that we are summing up refers to uh, the difference in the volume of the outer cylinder minus the volume of the inner cylinder, where I starts from 1 and end up to n, and n approaches infinity. Now, applying the rules of summation, we get volume is equal to the limit of the summation of 2 pi h sub I L sub I dH, where I equals, or I starts from 1 up to n, and n approaches infinity, plus the limit of the summation of pi L sub I dH square, where I starts from 1 up to n, and n approaches infinity. Simplifying further, by applying the rules of summation, we get this 2 pi, since this is a constant, so we have 2 pi times the limit of h sub L sub I dH. I starts from 1 to n, and n approaches infinity, plus pi, the constant of the second term, times the limit of the summation of L sub I dH square, where I starts from 1 to n, and n approaches infinity. And then simplifying or expanding the second term, we have, I'm referring to the second term, the limit of the summation of the L sub I dH starts from 1 to n, and n approaches infinity, times the limit of dH as n approaches infinity. We get 2 pi times the limit of the summation of h sub I times L sub I times dh, where I starts from 1 and up to n, and n approaches infinity, since the limit of dh as n approaches infinity equals 0, so that would make the second term equal to 0. And so what remains is the first term. And so we have the general formula in finding the volume of the cylindrical shell. That is, V is equal to 2 pi times the definite integral of h times L times dh from A to B, where h is the distance of the rectangular element from the axis of revolution or rotation. L is the length of the element or of the rectangular element, and dh represents its width. So take note. So we have the general formula in finding the volume of a cylindrical shell. Now let's have example number 1. To find the volume of the solid generated by revolving about the y-axis, the area bounded by y equals x squared, x equals 2, and y equals 0. So our axis of revolution or rotation is the y-axis. And what are we to rotate or to revolve about the y-axis is the area bounded by this 3. The function y equals x squared, the line x equals 2, and another line y equals 0. So first, we sketch the graph of y equals x squared. It's a parabola opening upward, and the line x equals 2. It's a vertical line. The line intersects the curve at point 24. Now we note that h, which is the distance of the lower base to the y-axis, is equal to x. And L, which is the length of the rectangular element, is equal to y. And the width, dh, is equal to dx. If we revolve this rectangular element about the y-axis, we get a solid of revolution known as a cylindrical shell. Using the general formula where h equals x, L equals y, and dh equals dx, we have volume is equal to 2 pi times the definite integral of x times y dx from 0 to 2. Take note of the integrand, it's xy dx. Since we are integrating with respect to the variable x, then we need to replace the variable y in the integrand. How? So to do that, we will use the function y equals x squared. So we substitute x squared to this y. So we have x times x squared in the integrand. And then we get this. Volume is equal to 2 pi times the definite integral of x cubed dx from 0 to 2. And then integrated, have 2 pi times the times x to the power of 4 over 4. Evaluate this from 0 to 2, and we get the volume, which is equal to 8 pi. So that is approximately 25 cubic units. Let's have example number 2. To find the volume of the solid generated by revolving about the x-axis, that is our axis of revolution or rotation. The area bounded by y equals x squared and y squared equals x. First, we sketch the graph of y equals x squared. It's a parabola opening upward. And graph of y squared equals x, it's a parabola opening to the right. Notice that the curves intersect at 0.11 and 0.00, or the origin. We note that h, which is the distance of the lower base to the x-axis, again, h is the distance of the lower base to the x-axis because our axis of revolution is the x-axis, okay? Not the other one. It's equal to h is equal to y, and L, which is the length of the rectangular element, is equal to x sub r minus x sub L. Because the left end of the rectangular element is x sub L units away from the y-axis, and its right end is x sub r away from the y-axis, and the width dh is equal to dy. So if we revolve this rectangular element about the x-axis, we get a cylindrical shell. Using the formula, or the general formula, where h equals y, L equals x sub r minus x sub L, and dh equals dy, we have 2 pi times the definite integral of y times x sub r minus x sub L dy from 0 to 1. Take note of the integrand. Our integrand contains the variable x sub r and x sub L, and we are integrating with respect to y. So we need to replace the variables x sub r and x sub L in the integrand. So to do that, we will use the functions y equals x squared and y squared equals x. Y equals x squared is the right curve. So expressing it in x in terms of y, we get x equals the square root of y. And if we substitute this square root of y to x sub r, or we substitute this square root of y to x sub r, on the other hand, y squared equals x is our left curve. And it's already expressed in x in terms of y. So we substitute y squared to x sub l. So we have 2 pi times the definite integral of y times the quantity square root of y, which is our x sub r, minus y squared, which is our x sub l dy, from 0 to 1. Simplifying this, we get 2 pi times the definite integral of y raised to the power of 2/3 minus y cubed dy from 0 to 1. Integrating the integrand with respect to y, we get 2 pi times the quantity 2y raised to the power of 5 halves over 5 minus y raised to the power of 4 over 4, and then evaluate this integral from 0 to 1. And multiplying the answer to 2 pi, we get the volume of the cylindrical shell, which is equal to 3 pi tenth, or that is approximately 1 cubic unit. Now, this requires constant practice and application to really master the procedures in solving the volume generated by revolving around the x-axis of rotation, or about the axis of rotation, the area bounded by a given function. To this end, I would like to remind you that constant practice doesn't make you perfect, but wise. Thank you for listening. Stay safe and healthy. This is Sir Pao. Goodbye.